Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to analyze motion of multiple systems constrained together in some way, shape, or form. So in this example, what we're looking at is this kind of set of pulley systems. And the point A here is moving down at 5 meters per second. I called that the velocity at point A. And what we're going to do is try to calculate the velocity at point B. So when we're dealing with systems like this, what we need to do is we need to decide how to measure different points in the system. So what I'm going to do is I'm going to put in a datum here. So this datum is where I'm going to measure my positions from. Now I could put the datum up top here, would be just fine. I'm going to go ahead and just put the datum right through the center of that pulley, and again, that's choice. You can put a datum anywhere you want in the problem. So that's going to be my datum. And now what I'm going to do is I'm going to label various distances in this problem. So the distance from the datum, since this is point A, I would go ahead and just call this distance A. And here's mass B here. I'm actually going to measure the distance to the center of that pulley. I'm going to call that distance B. I'm noticing that there's a distance here between these two pulleys that I think is going to show up. I'm going to call that H, I guess, because it's a height. Now, as far as how we analyze the problem, the system is connected together by a rope. And the important thing to recognize is if I follow that rope along, and I'm going to start at A. All right, this rope comes around here, and then it's tied off. And the important thing to recognize in this problem is the length of that rope is not changing. So the game plan here is I'm going to write an equation for the length of the rope. It's going to look like, L equals something. And then what I'm going to do is time differentiate it because the length is not changing. So I know in that equation the left-hand side will be 0. Now there's a couple other distances I'd like to point out. There's some sort of distance along this pulley here, and I'm going to give it a name. I'm going to call it R1 just because it's a radius and it's the first pulley I mentioned. There's a distance along here, and that's the second pulley I've mentioned, and that distance is along this curved path at constant radius. I'm going to call that R2. Here's another distance here. I'm going to call that one R3. So now what we do is we write an equation for the length of the rope, and I'm just going to start here at point A and work my way all the way around to this point right here. So as I move from A to here, well, from point A to here, the distance is what I called A. As I move along here, I'm adding the distance R1. We move down to here, we're adding the distance I called B. Along here, we are adding the distance R2. All right, now, from here to here is basically, let's see, that's equal to the distance B minus distance H. So I'm going to put plus B minus H. The distance along this pulley, R3. And then again from here to, now it doesn't matter where this thing's tied off. Imagine this thing is tied off at this point right here. I'm going to call this, again, distance B minus H. And bang, we've got an expression for the length of that rope. Okay, now I'm going to go through and time differentiate everything. So again, you got to imagine d dt of all these quantities here. So time derivative of L is 0. And then this thing's time derivative is A dot. This guy's time derivative is 0 because it's a constant in the problem. This guy's time derivative is B dot. This guy's time derivative is 0. Then we got another B dot. This distance not changing, so its time derivative is 0. This guy not changing, time derivative 0. Same thing with that very last H. So we're just going to have another B dot there. So we end up with this fairly simple equation between A dot and B dot. So we get A dot plus 3B dot is equal to 0. Now, whether A dot is positive 5 meters per second or negative 5 meters per second, well, it's kind of viewpoint. Depends on how you want to define A. If I define A as a distance, A is increasing, so A dot would be positive 5 meters per second. I could also define A as a coordinate, and if I measure from here with down positive, then A dot would also be positive 5 meters per second. If I define A as a distance, I do up positive, then A dot would be minus 5 meters per second. Now, going back to the way I set this problem up, I was interpreting A as a distance when I wrote this equation. The distance that I call A is increasing, therefore for A dot I'm going to put positive 5 meters per second. Then we're going to have plus 3B dot, and we can just solve that for B dot, and we're going to get minus 5/3 meter per second. Alright, the minus sign means the distance B is decreasing, which means that this point is moving up. The next thing would be to try to find accelerations. Accelerations are found pretty well exactly the same way. If I went through and differentiated this again, it would read 0 equals A double dot plus 3B double dot. Now if I had a value for A double dot, I could find B double dot, but that wasn't actually part of this problem, so this thing's basically done. Let's see, we could approximate this to, let's see, minus, what would that be, 1 2/3, minus 1.67 meter per second. So I would say as a final answer, B dot is 1.67 meter per second up. So hope this video helped demonstrate this concept. Have a great day.